Hi, my name is Nandita Jayaraj, and with me today we have Ramanujam R, a computer scientist who is more popularly known here as Jam. We're going to be talking about the Nobel Prize in Physics that was given out this year. And the 2024 Nobel Prize in Physics went to John Hopfield and Geoffrey Hinton for their foundational discoveries and invention that enable machine learning with artificial neural network. So, Jam, I want to start off by asking you to break down these two bits of jargon that I really struggled with, which was machine learning and artificial neural network. So, can you tell me what that means?
Well, if you are looking at the human brain, right, we process information all the time, right, from very small baby to. But how do we do it? I mean, we notice, we observe data. You can think of it as data. And then we have access to memory. So we recall. And we also put in learning, effortful learning, right? So through all this, we learn. Right? This is what we call learn. We also think.
Yeah.
Now, if you can build computers that access data, that observe, record data, and memorize, access to memory, you're doing quite a bit of these. Now, if you can also identify patterns and interpret, and from that make predictions on what is going to come, you've gone quite far. Now, whether that constitutes thinking is a different story. But this is typically machine learning. We should really call it computer learning because computers learn in this sense. They observe data, they store data, they have memory, and based on that, they make predictions. So this is typically what we call machine learning.
Okay.
And the idea of artificial neural network is that if you see the brain, again, it's inspired by the brain. The brain is made of neurons. We're not talking about millions and millions of neurons. Every neurons are connected to each other through synapses. And when a neuron fires, it sends a signal mediated by the synapses to other neurons.
Okay.
And at a time, a neuron is receiving signals from lots of neurons. That's what we call a neural network.
Okay.
This is how we understand the brain.
Okay.
Right. But at least it's a model of how we think the brain works.
Right.
I mean, brain is a mystery, but this is how we understand. So when you say a neuron fires, it's not like firing, but a signal being sent. So what causes one neuron to fire another is neuroscience. But this is neural network.
Right.
The artificial neural network is basically you model the same thing, but in computers, where each node or neuron you can think of as storing one bit of information, either a 0 or a 1.
Okay.
And then many of these are interconnected in some particular way. But what does this do for you? Think of it as, supposing I'm walking by on the street, some house, and some smell of sambar or fish curry or something. That immediately evokes a certain memory in you, right? We call this associative memory, right? So something is associated, and what that memory may have nothing to do with food, but it evokes a certain thing, right? Yeah. So this is what happens in artificial neural network. When some data comes in, it triggers certain patterns that are already stored.
Okay.
And so you recognize something,
okay,
right? And now you can also recreate patterns. Old patterns you can recreate and you can do. And then when you get some new data that is distorted or incomplete, you can refer to the old and correct it. So you can think of it as, for instance, an image.
Okay.
Right? A photo or something. That photo is actually just data coming into the network. That triggers associations. From that, sees stored patterns, existing patterns. And now, in the process, if a new pattern is found, that is also stored. That is the learning. Right? So there is neural networks. They can recognize data, patterns, images you can think of, create some. But then what about learning? Right? How do you learn?
Yeah.
How do you come up with new stuff? And there, something new you can see, right? I mean, for instance, you meet someone and you recognize the sibling of a friend. You never met the sibling.
Okay.
The first time you're seeing that sibling, right? But there is sufficient similarity Therefore, you are not sure. I think maybe it's, looks like so and so. That is something that, what's the probability that she is the sister of someone, of your friend? Right. So this is the idea. So now you bring in this kind of thing, and you can build further. Right. And that, so basically you can now not only get data, but you can categorize data. Right. You're building categories, right? Friend, sibling, all that. So the learning actually is some kind of conceptual learning also becomes possible. So I would say this is machine learning, neural learning through networks.
So this is, of course, in a sense, we're talking about artificial intelligence. And this concept, I understand that it actually originated quite early on in the early 20th century. And maybe you were telling me even before that.
Yes. I think in the 18th century, already people were fascinated by the idea of machines that can do reasoning. Leibniz, in fact, wanted to build a logic machine. And he, in fact, in a famous thing, he actually says, once we have these things, when people have an argument, they will not argue. They will say, let's calculate. Use the machines to resolve arguments. So this is the kind of daring ideas people had. But building such things was difficult. Lots of calculating ideas were there. In the 19th century, people actually, Babbage built machines, and people saw that you could calculate, you could do inference, you could do many things. Boole saw that. And Peirce even said that at some point, these would be thinking machines. Right. So these ideas were there. But it was really in the 20th century with Alan Turing explicitly asking, can machines think?
So I guess after the, the 50s, 60s, there was this boom in interest. And then I also read about this period that is now known as AI winter, sometime in the 70s, where there was this dip and this lack of funding and interest in artificial intelligence. And these two Nobel laureates are credited with reawakening interest in AI a bit, as far as I understand. So I thought, could we hear a little bit about what they did? And maybe we can start with Hopfield.
Hopfield was a physicist, and he was studying applications of physics and molecular biology. And he was looking at study problems and that, and was applying. In that process, I don't know whether he was invited or he attended a conference in neuroscience, and he was hooked. He saw these people talking about the working of the brain, this kind of neurons, these networks. Now, the idea of the kind of neural network that I talked about goes back much further, before Hopfield. McCulloch and Pitts in the 1950s, Halliday talked about models of neurons and networks of that kind. What Hopfield brought in was, I would say, see that whole network as a single thing. Now, this is something fascinating, and that idea really comes from physics. And, Hopfield had this physical insight. He had been working with magnetic materials, and in magnetic materials, there are these ideas that, each atom you think of as having a spin, the term they use. Now, but the point is that you have so many neighbors, the spins of your neighbors affect yours, right? And they can affect in a fancy or funny way, if you can call it, so that whole domain forms, right? Where everything is spinning in the same direction, if you will. So he had seen such properties. And then, therefore, he said, okay, maybe I can think of the overall state of the neural network also. I describe as if there is something like a, system energy. I mean, I'm just saying, inspired by physics, right? So he came up with a formula that sees the whole network and that takes into account all the nodes and all the interconnection strength between each of these nodes. So this is what I mean by seeing it in one unified way. And in that process, he showed that, networks of things with just zeros and ones could retain memory, associate. So memory is something emergent from the network, as the state of the network. So you can think of, so what is it that we call memory? It's a state of remembering.
Yeah.
right?
Yeah.
So in different states, you remember different things. That's what it is. That's exactly what Hopfield showed. He showed that you can remember things. In particular, for instance, back to your image, there's a photo or something like that, and the data comes into the network through various this thing. The network configuration changes in some way to look at the patterns, and that is a memory of that.
And this
And
is
so
what
you
is
can create patterns, you can find new thing, all this.
right.
Yeah.
And this is what we call a Hopfield network.
Hopfield network.
Okay.
And this is used to talk about this kind of networked things in physics, in many, many different things. But in particular, for machine learning, it turned out to be a very, very important idea. But this idea of memory is, I think, really what Hopfield actually gave.
Right.
And that you can memorize patterns
Right.
and recreate patterns, store patterns in just this. This is very different from the way, we memorize tokens and recall and so on, right? There is no conscious effort. It's just the state.
So at what point did Hinton come in? And I also heard that Hinton is sometimes referred to as the godfather of AI. So what did he do?
Yes. Hinton, when he heard about, I don't know whether he read it or heard about Hopfield's work. At the time, he was in Carnegie Mellon University. He had worked in England and Scotland in fields like experimental psychology, computer science, and artificial intelligence, really. As I said, artificial intelligence was an established field.
Right.
We're talking, Hopfield's paper is 1982. And so this is 80s that we are talking about. After AI had already had glory days. There was a lot of hype about AI in the 60s. What you called the AI winter is because technology couldn't keep up with the promises, funding dried up. Said, you promise big things and you're doing tiny stuff, right? So technology had to change. So this is the situation when Hinton got into the thing. And Hinton's brought in a very important idea in this thing. It's one thing to remember patterns. But so memory is okay, but what about interpretation?
Okay. Yeah.
Memory is still passive. How do you interpret data? I want to store images, but I also want to interpret images, right? So how do I look at that image and say, this is a cat, this is a tiger, or a tiger cub, not a cat? I want that distinction, right? How do you do that? So one important thing that Hinton brought into the picture is that, I take the state of the network, but I also look at it in a probabilistic way.
Okay.
Right. So this is one. So you want to look at the states. So I want to say that something like this. This I should also mention. His name is Sejnowski, his collaborator. It's not just Hinton. Right. Hinton and Sejnowski together said, some states are more probable than the other.
Okay.
Right. In the and now how do you decide how much, which state is more probable? And well, you think of it as that depends on the amount of energy available in the system.
Okay.
Again, they used physics to do this, and they were really inspired by this 19th century physicist Ludwig Boltzmann.
Okay.
And so they used the Boltzmann equation to describe this distribution of states of the network. And that turned out to be they called it the Boltzmann machine. Okay. And it turned out to be a very insightful thing. See, it's a bit like this, that every pattern, we're talking about storing patterns, right? Now what you are saying is that every pattern has a certain probability. Right? Given this information, is it a cat?
Right.
That's why you're able to interpret things in a better way.
Yeah.
Right? I say, given this information, chances are that it's a cat. If I change it a little bit, chances are that it's a tiger. So I can attach categories to all this, classify stuff and do this. This is very important for learning, and it is a major breakthrough in that sense. Right? And what is very interesting is that now you can generate new patterns. So if you were to think of a network, information is flowing in one direction. You think of it as input going to the output, right? And one thing that Hopfield and Hinton and co-workers brought into the networks is this idea of that, okay, there are layers of things in between. Some are hidden, some are visible layers. The hidden layers are very important because they contribute to the energy of the system. Right? They balance and they can contribute to that. So, but then you not only move things forward going from input to output, you can say, what about running it in reverse? So they call this feed forward back propagation in this area. And it turned out to be a very powerful idea. Well, by this time, it's Hinton, co-workers, more people getting into the act. Many people were involved. But this idea changed the thing quite dramatically because I started with this photo, with this image. From that, I have figured out categories like cat and, there is a pole nearby, the cat. And then there is a baby. I figured out all that. And now I say, can I take this and do the whole thing in a reverse way so that I want to generate an image of a baby driving a car. Car is some neuron somewhere, baby is here, and I have seen baby sitting in a pram. But now I combine these two patterns and I generate one. Now you see the power of generative AI. I can generate a photo which has got a baby driving a car, which you couldn't have generated. So this idea that, it is not just the Boltzmann machine, but then later people came up with what they call the convolutional neural network, which did more of all this kind of representations and these. But this powerful idea already gives you generative AI, right? You are able to see data, and now when you have, at the time with 80s, 90s, they could do this. People could already see that this is good for image recognition, speech processing, but technologically it kept running into bottlenecks. Then certain things changed. Again, Hinton contributed in the 90s in a very important way, what they call reduced Boltzmann machines, RBMs they are called, reduction or reduced ones, where this is more mathematical. You just look at the distributions, look at the waveforms, some way of optimizing, so that people could think of many, many layers in between. That is the deep learning, as they call it. Deep learning dramatically improved the technology. The other big change that happened going from 90s to 2000s is big data. Everybody started using the mobile phone, social media. All of us are contributing data all the time. Every time you use WhatsApp, you are giving data to the world, right?
Whether we know it or not.
Right. So big data. So these machines suddenly could learn enormous amounts, right? So one hand, technology changes, but remember this learning requires data. Who's going to provide the data? Earlier, academic laboratories producing data. Now, no problem. So I would say that that's why in the last, and then another major breakthrough came, which has nothing to do with these people, which is the transformer architecture. GPT today, that's it. The T is for transformer.
So that's the hardware aspect of it, or it's still the...
Again, software. It's linear algebra, vector spaces and so on. But they came up with a very dramatic idea. This is very recent. That's why, another major change has happened. But Hinton and Hopfield gave the original, main idea goes back to Hopfield. And I think the very important breakthroughs come from Hinton and co-workers. There is a team of several people who have done that. And the other people who did convolution, they got the Turing Award along with Hinton a few years ago.
I also have to ask you this, Jam. I think among all the science Nobel Prizes, physics took everyone by surprise because it was given for this AI discovery, which is not something we typically think about when we say physics. And just looking at the background of the laureates themselves, and you mentioned this also, that Hopfield, though he had a background in physics, he then became a professor of chemistry and biology, and then he went into AI. And Hinton also has a background in psychology and statistical physics and AI. So, like, what is happening here? What do you make of this? I don't know if I can call it a trend, but...
Yeah. So, one thing is that this is certainly work that is deeply physics inspired, right? This is really physics ideas coming into AI. That's much is clear. And without the statistical physics breakthroughs, all the other technological breakthroughs couldn't have happened. That's for sure. And then conversely, this kind of work has led to very important changes in the way physics is done.
Okay.
Right? I mean, this kind of neural networks have contributed to study of quantum many-body problems. Then other things in like, the Ice Cube neutrino project has given a neutrino map of the Milky Way.
Okay.
And we have had this recently where the black hole in the center of the galaxy, Milky Way galaxy, this is found using the, these kind of techniques.
Okay.
So it's found dramatic applications in physics, used routinely now in the Large Hadron Collider, Higgs boson, many of these, they do. So it's extensively used.
Right. Even the Nobel in chemistry.
This is the most dramatic one, AlphaFold, right? Protein folding, which is considered one of the most hardest problems. This kind of AI is able to solve.
Right.
So that is true. But of course, I don't know other Nobel Prizes in physics that have gone because of inventions. To some extent, it's almost as if the Nobel Committee decided that it should be given to AI, and because the neural network applications have been around for quite some time in physics, and the fact that it's physics inspired has been. It's so I would say it's the committee deciding to give it that. Whether it is for physics in that sense, I think is, there is some debate. And why not? You can say, another ways to look at it is that, we should extend physics to think of everything, all that impact it's having in the world, maybe.
All right. Thank you so much, Jam, for helping me break this down, because I certainly could not have done it without you.
Thank you very much.
We hope you enjoyed listening to this explainer of the Nobel Prize in Physics. If you like such explainers and you would like to hear more about other science awards in the past years and also this year, make sure you go to the Azim Premji University website and also our YouTube page. Thank you for watching.